Before we begin the notes for section 2.1, I just want to remind everybody to read the section before looking over these notes. These notes are a summary of what I feel are the most important points of the section, but it's still important to read the section, get a basic understanding for the section on your own before going over these notes. Hello everyone, Mr. K here, going over Unit 2/12, Atomic Structure. This is just an introduction to the unit. This might be helpful when you need to go back and review these units at the end of 2 years, just to see what the unit is about. In short, it's about atoms and how atoms make up everything. How atoms of the same element have the same chemical properties, and atoms of different elements have different properties. We're going to talk about, well, what makes an atom of oxygen an atom of oxygen? What makes an atom of carbon an atom of carbon? And then how do we determine what the properties are of these different elements? We'll also understand how the subatomic particles are arranged in atoms, the subatomic particles being neutrons, protons, and electrons. And we're also going to talk about how quantum theory can be used to explain how the particles behave, like waves. Sometimes particles behave like particles, and sometimes they behave like waves. So we'll use quantum theory to talk about how to explain the behavior of particles that can only be explained when they act like waves. Section 2.1 should take about a day and a half to cover in class. Therefore, I recommend you watch the entire section now, so that in case we go through the section faster than I planned. Section 2.1 is called the nuclear atom. A substance of a single element has the same chemical properties regardless of how much of it there is. Atoms, and atoms are the smallest unit of any one element. Atoms of the same element all act, behave, react, have the same makeup. We're going to talk about Dalton's view of matter. He was the first one to go from the shift of an old way of thinking about matter to this idea that that matter is composed of atoms. John Dalton noticed that hydrogen and oxygen always combine in fixed proportions. And so to explain this idea that you always had two amounts of hydrogen and one amount of oxygen always combining together in certain ways, he said, well, I think that all matter is composed of tiny, indivisible particles called atoms, that these atoms cannot be created or destroyed, that atoms of the same element are alike in every way, atoms of different elements are different, and atoms can combine together in small numbers to form molecules. Now, most of this is true and accepted to be true today. There are some small things like atoms cannot be created or destroyed. That's true for chemistry, for chemical reactions, but we'll find out later that that's not always true for other types of reactions. And atoms of the same element are alike in every way. There are some slight differences, but they still have the same chemical properties, even though they'll be slightly different. And we'll talk about how atoms of the same element can be a little bit different. But this was revolutionary when it first came out, so revolutionary that it wasn't accepted at first. Only after having done more and more experiments did the scientific community come to understand that most of these ideas are indeed true. So how do we have so many substances? Well, we have about 100 elements, and they combine in just different ways, different combinations, different types, different amounts of different elements combined to form new substances. And the combination of more than one element is called, or more than one atom, is called a molecule. So for example, using this water example that Dalton had, 2 atoms of hydrogen can combine with 1 atom of oxygen to form 1 molecule of water. And as he proposed, it doesn't matter how much you have of the substance. So you can have 2 times 6.02 times 10 to the 23rd atoms of hydrogen combining with 1 times 6.02 times 10 to the 23rd atoms of oxygen to form 1 times 6.02 times 10 to the 23rd molecules of water. And that's the exact same as, if you notice, 6.02 times 10 to the 23rd is Avogadro's number. So those numbers, these numbers right here, 6.02 times 2 and 6.02 times 1, it's the same thing as saying 2 moles of a hydrogen combined with 1 mole of oxygen to form 1 mole of water. If we convert the moles to grams using molar masses, we can say that using things we can measure in the lab, we can measure grams in the lab. 2.02 grams of hydrogen combined with 16 grams of oxygen to form 18.02 grams of water. So the first person to delve into the idea of what an atom looks like was J.J. Thomson, and he discovered the electron. He discovered it by using a cathode ray tube. What he ended up guessing, and he's wrong, but it was heading in the right direction, is that there's this mass of positively charged stuff, kind of like a sponge in a way, a spongy, slightly positive charged material, and inside there were little specks of higher concentration negative. So you have this light positive charge mass with little specks of electrons, these little particles of electrons that were inside this mass, and this is called the plum pudding model. Rutherford discovered the proton, and the experiment he used to discover the proton was by shooting alpha particles, and what an alpha particle is a helium nuclei, 2 protons and 2 neutrons together. So therefore it has a charge, has a positive charge. He shot it at a piece of gold foil. Based on Thomson's model, he would have guessed that they would have gone through or gotten stuck in that spongy material. What he noticed was most of them did go straight through, which wasn't the biggest surprise in the world. He found that some were deflected and bounced back, which is unexpected, which led to the idea that, well, an atom is mostly empty space with a small, dense, positively charged center, the nucleus, and we now know this to be true. The nucleus is made up of protons and neutrons, called nucleons, together. So a nucleon is either a proton or a neutron. They both have about the same mass, that is, a proton and neutron have about the same mass, and they make up most of the mass of the atom. An electron has an equal but opposite charge to that of the proton, but it has much less mass. In fact, an electron has so little mass that we typically ignore it when calculating the mass of atoms, or when calculating the molecular mass of a molecule. And here's a chart that shows you the relative masses are 1, 0.0005, and 1. So we typically just ignore the mass of the electron. The electron is important because it has a charge that is equal to but opposite that of the proton, and the neutron has no charge. This is a nature of science point brought up by your book. We now know that this explanation, the one I just described about an atom, is not exactly true. The subatomic particles of the neutron, proton, and electron aren't the smallest ones that exist. There are smaller ones that we won't talk about in this unit, but this basic model is good for our needs. We're even going to use models that are less accurate because they help us explain basic concepts. So models that are found to be not exactly 100% true are still important if they can help explain other things. If they can help explain more complicated processes, for example, bonding, even though they may not be 100% accurate. That's a nature of science question or concept. The Bohr model of the atom was developed by Niels Bohr, and he said, what I think it is inside the middle, this neutron, in the nucleus is where the protons and neutrons live, and the electrons orbit the nucleus, kind of like a solar system, like how planets orbit the sun in a solar system. And here we have an example of a hydrogen atom with its 1 proton and 1 electron, and here we have an example of the helium atom with 2 protons, 2 neutrons, and 2 electrons that are orbiting it. And as mentioned, this is not, we'll use the Bohr model to explain how different atoms of different elements react and share and give electrons away, even though we found out that this is a very simplified version of what happens. In fact, electrons don't orbit the nucleus, and like planets orbit a solar system, it's more complex than that, but this basic model helps us explain a more complicated concept more easily, like bonding. There are 2 numbers associated with any atom, the atomic number of that atom, and the mass number of that atom. The location of elements in general in the periodic table is due to one of those numbers, the atomic number. And the atomic number is given the letter Z to represent it. This defines what kind of atom it is, and it's the number of protons in the atom. So any atom of any one element has the same number of protons. Since an atom has no overall charge, this is also the number of electrons for atoms. The mass number is the number of protons and neutrons in the atom added together. So the atomic number is the number of protons, and that defines what the element is, and the mass number is the number of all the subatomic particles that have mass, or significant mass, the protons and neutrons. The electrons, again, have mass, but it's so small we ignore them. So the mass number is the sum of the protons and neutrons, A, and the atomic number, Z, is the number of protons in an atom, which, for atoms, equals the number of electrons. We write this, for example, for aluminum, like this. We have aluminum, the element symbol, placed in the center or just located, and in the top left, relative to the symbol, in the top left is the mass number, and the bottom left is the atomic number. So for aluminum 27, which is a certain isotope of aluminum, it has a mass number of 27, and all aluminum has 13 protons, therefore its atomic number is 13. So based on this information, we can calculate how many protons, neutrons, and electrons an atom of aluminum 27 has. 13, the atomic number, is the number of protons and electrons, and 27 is the number of protons plus the number of neutrons. So the neutron number, the number of neutrons, would equal the total number, 27, minus the number of protons, which we get from the atomic number, equaling 14. So the number of neutrons is 14, the number of protons and electrons is 13. There are two main pieces of information about atoms given in the periodic table. That is, their atomic number and their relative atomic mass. As we stated in the previous slide, for any one given isotope, it has a whole number mass. The mass number is the mass of that isotope. What occurs in nature is there are different isotopes of the same element. For example, aluminum exists in nature as aluminum 27 and aluminum 26. So there are some aluminum atoms that have have a mass number of 26. That is, they have 26 neutrons and protons added together. They have 13 neutrons. And then some of the atoms are aluminum 27. Now, the overwhelming majority of those atoms are aluminum 27. 99.9% of all atoms are aluminum 27, and about 0.1% are aluminum 26. So when we look at the periodic table, these two pieces of information, the atomic number and the relative atomic mass, we can see that the atomic number is the number of protons, therefore it's 13. And the relative atomic mass is an average mass of all the isotopes. So since aluminum has isotopes of aluminum 26 and 27, it's somewhere between 26 and 27, and since there are many, many more isotopes of aluminum 27, the mass is closer to 27 than it is of 26. We can calculate this if we know the percent abundance of each isotope of an element. Now it's important to note that the chemical properties are based on the number of protons. So even though aluminum 26 and 27 have different masses, they react the same way. They behave the same way because they have the same number of protons. And we're going to go ahead and do a calculation to find the relative atomic mass of chlorine using the weighted average of, if it's two isotopes, having known the percent abundance of each of those isotopes. All right. The first problem we're going to do involves chlorine isotopes. Chlorine comes as two isotopes, chlorine 35 and chlorine 37. We're given the abundance of each of those. We're told that the abundance of chlorine 35 is 77.5%, and the abundance of chlorine 37 is 22.5%. So to calculate the relative atomic mass, we have to multiply the mass number by the relative atomic the abundance, and add to that the mass number of the other isotope times the abundance of that isotope. So the relative atomic mass is equal to 35 times 0.775 plus 37 times 0.225. So I'm converting the percentages into decimals. I'm going to do this all in one swoop. I'm not going to do these calculations separately. I'm going to do it all together. 35 times 0.775 plus 37 times 0.225. Double check my numbers are correct and hit equals. I get 35.45. So the atomic mass for chlorine is 35.45. Ions are similar to atoms, except they have more or less electrons. The electrons are the only thing that changes or moves during a chemical reaction. If an atom loses or gains electrons, then the number of protons and electrons in that atom is no longer equal, and the atom has a charge. When an atom has a charge, we call it an ion. Atoms that lose electrons have a positive charge, and they're called a cation. Atoms that gain electrons have a negative charge, and they're called anions. We can write the symbol for an ion. For example, aluminum as an ion has a 3 positive charge. And it's written the same way as we wrote the aluminum atom, except we put the charge here in the top right-hand corner. This is for aluminum 27, so its mass number stays the same, its atomic number stays the same, the number of protons doesn't change, but because it now has a charge, the number of electrons has changed. So we would find that the protons are still 13, the neutrons for aluminum 27 is still 27 minus 13. The total number of protons and neutrons minus the protons gives us the number of neutrons. However, we have to do an additional calculation to find the number of electrons. The number of electrons is simply the number of protons minus the number of electrons it's lost. In this case, since it has a 3 positive charge, it lost 3 electrons, so the number of electrons on an aluminum 27 ion is 10. Similarly, atoms can gain electrons. Oxygen, when it's an ion, has gained 2 electrons. Again, this number tells us the number of protons. The atomic number tells us the number of protons. The mass number tells us the number of neutrons plus protons. So if we have 16 neutrons and protons added together minus the 8 protons, this tells us that this oxygen ion has 8 neutrons. To find the number of electrons, it's simply the same number of protons plus the charge, plus the 2 extra electrons it has. So 8 protons plus the 2 extra electrons, because it's the ion form of oxygen, tells us that oxygen 16 has 10 electrons. And we're going to do a couple more problems. So this is a problem from your book, page 65. It asks us to identify the subatomic particles in radium-226. It's an isotope of radium. What we'll notice is the mass number is written down. It tells us the mass number is 226, but there's a gap here. There's no atomic number. But that's okay because all isotopes of radium have the same atomic number. We can find that on the periodic table. If we go to the periodic table and look at radium, chemical symbol Ra, we can see that its atomic number is 88. So we can add that piece of information here. So the number of protons is equal to 88. The number of electrons, since it's an atom and not an ion, is equal to the number of protons, which is 88. And the number of neutrons is equal to the mass number minus the number of protons. 226 minus 88 is 138. So this is the number of protons, electrons, and neutrons in radium-226. Another problem in your book, same page 65, asks us identify what the substance is, or what the element is, that has 19 protons, has 20 neutrons, and 18 electrons. What is this? Well, we're going to start with the 19 protons. The number of protons tells us what element it is. If we get our periodic table out and go to the element that has an atomic number of 19, we can see that that's potassium, K. Potassium K has 19 protons. So that number goes there. The mass number is the number of protons plus the number of neutrons. We have 19 protons plus 20 neutrons gives us 39, a mass number of 39, or 39 nucleons. So that goes there. If we notice, the number of electrons is 1 less than the number of protons. So our atom isn't an atom at all, it's an ion and has a charge of +1, since there's 1 more proton than there is neutron. There's our symbol for our potassium ion. Another problem from our book says we have a calcium ion. It's present in many, many foods, and it asks us, we have a calcium 40 ion isotope, and it asks us, tell me the number of subatomic particles in this. So the first thing we're going to do is we're going to start with the one that's missing, the number of protons, which is the atomic number. We get out our periodic table and see that calcium has an atomic number of 20. It's a little out of focus, but it is 20. So the number of protons is 20. The number of neutrons is equal to 40 minus the number of protons. So it's the mass number minus the number of protons. The number of neutrons in calcium 40 2 ion, calcium 40 ion, is 20. And the number of electrons would be equal to the number of protons. Since it has more protons than electrons, we have to subtract that to show us that it has 18 electrons. 20 protons and 19 electrons would give it a positive 2 charge. That's the end of that problem. Now the book mentioned the exact mass of a proton and the exact mass of a neutron. It's some very, very small number. It's so small that it's not very practical to use, so that's why we use relative atomic mass. And it's all relative to carbon-12. Carbon-12 is chosen to use because it's common, it's easy to transport, and it's easy to store. The relative atomic masses, as I showed already, are recorded on the periodic table. We can use a mass spectrometer to determine the number of isotopes inside a certain substance, the mass of different isotopes inside different substances. The results from a mass spectrometer are called a mass spectrum. We can calculate the atomic mass for different substances. Here's what the book did. I'm going to go ahead and show you how I did the same calculation a little bit differently, but of course got the same answer. This is an alternative way to do the problem I just showed you on the slide. It's from page 67 of your book. It asks us to find out the relative atomic mass of rubidium given certain information. And it says the ion of rubidium that has a mass number of 85 has a 77% abundance. The isotope, did I say ion for that one? I meant isotope. The isotope that has a mass number of 87 has a 23% abundance. And so find out what the atomic mass is, or the relative atomic mass. The atomic mass is equal to the mass number of the isotope times its percent abundance. And that's true for both of them. You add to that the mass number of the other isotope times its percent abundance. And again, I'm converting the percentages into decimals. Plug all of that in my calculator. 85 times 0.77 plus 87 times 0.23. And I get 85.46. The atomic mass of rubidium is 85.46. We can also calculate the percent abundances of two isotopes if we know the relative atomic mass. And again, I will do this calculation slightly differently. Right, another problem from the book, the next page, page 68, asks us to find the abundance of the isotope. So it's similar to the problem we just did, but in reverse. But it is a little more complicated because of that. It tells us that boron exists as two isotopes, boron 10 and boron 11, and to use the periodic table to figure out what the percent abundance of these two are. So we're going to go to the periodic table for boron and see that its atomic mass is 10.81. So we use the same equation as before, except we just have a different unknown. The atomic mass is equal to the mass number times the percent abundance plus the mass number times the percent abundance. Now what's the percent abundance of the second one? Since we know there's just two isotopes, the percent abundance of the second one is 1 minus the percent abundance of the first one. So we're just going to go ahead and solve this equation. X will give us the percent abundance of boron 10. 1 minus X will give us the percent abundance of boron 11. Combine like terms. Subtract 11 from both sides. Actually, what I'm going to do is I'm going to put X over here and subtract 10.8 from both sides. So I'm going to add X to both sides and subtract 10.81 from both sides at the same time. Plus X minus 10.81. That gives me positive X on the left side equals 11 minus 10.81, 0.19. So the percent abundance of boron 10 is 19%. And 1 minus that would be 81% for boron 11. And that is the end of our section 2.1. Tomorrow we'll go ahead and do problems in class over this section. We'll answer any questions you have over some of the theory you didn't understand. And that's it. Hope this was helpful.